The topic of my talk is Rydberg state will chirp pulse millimeter wave spectroscopy. Okay, in this talk, I will briefly introduce our motivations and our apparatus chirp pulse millimeter wave spectrometer, and then I will show some experimental result and about Rydberg transitions of calcium atoms. To fully understand all the spectrum and dynamics of this experimental result, we have to consider about the cooperative radiation effect. That is very important, especially in some dense Rydberg gas. And at last, I will just try to propose to expand our chirp pulse technique to the Rydberg molecules. So the goal of our current project is to understand how the energy exchange between the electron and the nucleus. The Rydberg state is good for this study because in the Rydberg state, electron motion frequency can be tuned to resonance with nuclear motion frequencies. So in this regime, the non-adiabatic interaction is pretty strong, such as electron vibration and electronic rotation energy exchange. So what were our favorite molecule is calcium monofluoride, because it's a simply chemical relevant not atom. It, like an alkali atom, has only one electron outside the closed shell ion core, but the ion core is not ground. It has a very large dipole moment. So there is very strong R and E dependent. So in this way, it gives us a good opportunity to study the mechanism of electron and nuclear energy exchange. So our conventional technique in our lab is use optical double resonance ion detection. So we use a tunable pulse dye laser, two tunable pulse dye laser to prepare the Rydberg state. In the left situation, the Rydberg state is above the ionization threshold, so it can be auto-ionized. And in the right situation is below the ionization threshold. To compete with the pre-dissociation, we have to use very strong probe laser to use a multi-photon ionize it. And after the Rydberg electron is ionized, we use a pulse electrofield and a couple of ion optics to accelerate and focus the ion into the ion detector. So this technique, the resolution is determined by our current laser resolution is about 0.03 wave number. And because this is, there is some relative large fluctuation during the long time scanning, so our relative intensity is not so reliable. Relative intensity of different peak is not so reliable. And this laser is always near IR laser or optical frequency. And that will couple the two very different states with two different sets of good quantum number. So we do not have a very good, well-defined spectroscopic pattern to help us to do the assignment. So the assignment of the spectrum is pretty hard. So because of this disadvantage, we cannot resolve the hyperfine structure. We cannot separate quadrupole and polarizability. And it's very hard to do the assignment. And intensity information is not including in our fitting model. So to overcome such difficulties, so we are now using the new technique, the chirp pulse technique, to induce and record Rydberg transitions. We use some electronics to generate the 10 gigahertz bandwidth broadband chirp to induce all the transitions covered in this frequency regime to polarize the Rydberg atoms or molecules and then record it for induction decay. So this is a direct transition detection. We do not need to detect the ion, and we detect the millimeter wave photon. So we do not need high voltage ion detection system. So the Rydberg enemy straight electric field is automatically minimized. So different from frequency scanning experiment. In this experiment, one shot millimeter pulse will cover 10 gigahertz bandwidth. So it can we can record it the whole spectrum in one shot in principle. And in the detection resolution is about 100 kilohertz resolution. So that means in one shot we can detect about 100,000 frequency component. And we detect the signal in the time domain. So if we do the Fourier transformation into the frequency domain, so the relative intensity of the different peaks is pretty meaningful. It can up to 1% accuracy. So, and mean per wave always couples the neighbor Rydberg state, so which have very similar good quantum number. So the the spectrum assignment is almost automatically. And later I will show that we use arbitrary wave generator to generate these poles. So this pole we can arbitrarily manipulate the pulse, generate a pulse sequence to manipulate the quantum coherence. So this is our chirp generation and the free induction decay detection system diagram. We generate a low frequency broadband chirp by an arbitrary wave generator and mix it with a 10 gigahertz fixed frequency local oscillator, and use a single sideband filter to choose upper sideband or lower sideband of our mixing signal, and send it to a multiplier chain, active multiplier chain. This active multiplier chain not only multiplies the frequency, but also multiplies the bandwidth. So after that, we can get a 70 to 84 gigahertz or 87 to 102 gigahertz, 30 millivolts chirp pulse. So then we let its pulse interact with the molecules in the vacuum chamber, and use another gain horn to detect the chirp pulse and free induction decay, and mix this free induction decay with a 75 gigahertz GAN oscillator to down convert the frequency below 12 gigahertz, and read it by a fast oscilloscope. So to make sure that we can average the signal in the time domain without significantly phase drift, we use a 10 megahertz standard oscillator to log all the frequency generation and detection. Okay, this to test the performance of our spectrometer. So we compared it with traditional pulse mean per wave spectrometer to show that we have some improvement. So this is absorption spectrum of OCS molecules. So this is recorded by the bolometer detected absorption spectrum, and the bandwidth of this spectrum is about 100 megahertz. Signal noise is 700, and acquisition time is 100 minutes. So this is the same spectrum, but recorded by chirp pulse, and we get a bigger bandwidth, a 4 gigahertz bandwidth, and signal noise is a little bigger, and acquisition time is 50 minutes. So the resolution of these two spectrum is similar, but the bandwidth, this chirp pulse technique have much more bandwidth. So the more bandwidth give us a lot of other informations, like this is isotope shift. This peak comes from the hot vibration band. So to evaluate the improvement of this performance, we consider about the bandwidth, signal noise, and acquisition time. We find that the total improvement is about 400. That is a big improvement. Okay, so in next several slides, I will use this technique to induce the Rydberg transitions in calcium atom system. So this is our diagram of our experiment. We use two pulse dye laser to prepare the Rydberg state with a principal quantum number is 30 to 60. And then use chirp pulse to induce up transition or lower transition and recorded the free induction decay. So this is our first experiment result. We use a 10 nanosecond, 500 megahertz chirp to induce the polarization and recorded free induction decay. Oh, sorry. And recorded free induction decay here. And we do the Fourier transformation in the frequency domain. We get one peak with the resolution is 400 kilohertz, and side peaks is come from the Earth's magnetic field we have removed now. And these techniques have very large sensitive that we can achieve a signal noise is more than 10 in a single chirp without any average. So the line width of this the resolution and line width of this technique is determined by a lot of factors. In most of our experiment, it is dominated by Doppler broadening. So we find that in argon gas supersonic expansion. So our Doppler broadening is about 250 kilohertz. And later I will show that if we use a buffer gas cooling slow beam technique, that we can decrease the Doppler broadening to 50 kilohertz. And black body radiation also contributes a line width about 50 kilohertz. And if we can cool down the vacuum chamber, we can decrease it. And the dipole-dipole interaction and the superradiance are both strongly number density dependent. So in our experiment, it can tune from as low as 20 kilohertz to more than 1 megahertz. It's dependent on our number density of our system. So in the frequency domain, like this spectrum, we can see a peak, we can find the frequency, the resonance frequency, but we cannot point out that the transition is up transition or down transition. But we can point out that direction in the time domain. We have two methods. One is that we observe nutation. This is absorption nutation. This is emission nutation. Absorption nutation means that it's up transition. Emission is down transition. Another thing is that we can measure the phase difference about excitation pulse and the free induction decay. If the phase difference is pi, that's up transition. If phase difference is 0, that is down transition. And this spectrum is a mean wave photon echo spectrum. I show that because I want to use this technique. This is a very classical technique to measure the homogeneous decay when the inhomogeneous decay mechanism is dominated. That is very important for the for study the dipole-dipole interaction and the superradiance. That is both homogeneous process, decay process. So we use a 10 nanosecond pulse to induce polarization, pi over 2 pulse to induce polarization. And after the free induction decay is go away, and we use a pi pulse to reverse the phase and wait for the same time we see the refacing node. And if we change, we measure the different delay, a series delay time, and feed the amplitude of this node with different delay, we can just measure the homogeneous decay. This spectrum is inhomogeneous dominated. It's Doppler broadening, but we can measure the homogeneous decay is about broadening is 150 kilohertz. And this is chirp absorption spectrum. We use this black curve is 500 nanosecond, 500 megahertz broadband chirp without interaction with molecules. The red curve is interaction with molecules. We find that at the center, it's just a resonance absorption. And after that, we see a beat pattern, a ring pattern. That ring pattern is come from the beating between the chirp pulse and the free induction decay. So this, we like this method because it can detect fast process during the minute wave pulse with moderate high resolution. Because this is just 500 nanosecond, we do not need to wait the chirp pulse is finished and observe the free induction decay. We can observe the absorption during this excitation chirp. And another thing that in this spectrum, we can simultaneously measure the transition dipole moment and number density. The number density comes from the depth of this absorption part, and the transition dipole moment can fit from this curvature of non-resonance excitation part. Okay, in this slide, I will show an example about use millimeter wave pulse sequence to climb from low to climb up to high L state of the Rydberg state. So this is very useful for Rydberg molecules because I will discuss later. But here I will show this spectrum is doing in the atoms, in the calcium atoms. We use laser to prepare the 57D state at first, and use three pulses with different frequencies to try to climb up from D state to H state. So we artificially make that three pulses is not perfect pi pulse. So that means the three pulses not only induce population transfer, but also induce a polarization. And we can detect in free induction decay to show that this happened. So in this spectrum, we find that D to F, F to G, and G to H transitions. In principle, we can do more and climb up to even higher L state. Okay, So before, up to now, all the spectrum I show can be simulated based on very simple model that will assume that all the atoms or molecules is excited and radiated independently with each other. In the Bloch sphere, it can be explained by use power 2 poles to induce a polarization. And this polarization will process in the xy plane, and the amplitude of this polarization will be decreasing with free induction decay radiation and other defacing mechanism. But in a very dense Rydberg gas with kilodebye system, this independent model is not always right. So, because in a very dense Rydberg gas with large dipole moment, sometimes radiation is comparable with the excitation. So, two atoms or more atoms will try to share the same electric field and excited and radiated cooperatively. So that this model can be described in the Bloch sphere in this way. We use the same power 2 poles to induce a polarization. And this polarization will not only limit it in the xy plane, but in a 3-dimension. It's a 3-dimension spiral in this Bloch sphere. So the coherence radiation energy is not only come from the polarization, but also come from the population transfer, internal energy of the population transfer. So we see that this the population is in the z direction. So in the process of the free induction decay, the population is not changed. But in this model, the population is changed. So this type of the radiation, we name it cooperative radiation. So we have very different properties of the regular free induction decay. That radiation can be comparable or even bigger than the excitation. And the radiation decay is not always determined by the T2 time, the coherent decay time, but sometimes is determined by T1 time, but population decay. So the polarization can be self-amplified, and the frequency and phase can be modulated. So to use this model, we just do some numerical calculation to predict what phenomena we can observe in our experiment. So we do a very simple calculation. We just it's based on the semi-classical approximation, and we numerically solve the Bloch equation and the reduced wave equations. The cooperative effect is including in this calculation, because here the electric field is not only the excitation electric field, but with radiation electric field. So in the calculation, we do many cycle iterations to obtain the self-consistent local effect electric field. So, but in this calculation, we do not including the dipole-dipole interaction, and all the homogeneous decay is in this T2 decay time. So it will just shorten the lifetime of the radiation, but not induce any other effect like the frequency shift. So we use this program to calculate some examples to show that we may see the very significantly cooperative effect in your experiment. So first one is that we calculate the inverted 2-level system. So at time 0, we populate all the population in the upper state, and then we use a very small weak chirp to induce a tiny polarization, and then after that we observe the free induction decay. So when the number density is pretty low, we see that free induction decay is just single exponential decay. And we do the Fourier transformation, we find that it's regular Lorentz line shape peak. But if we increase the number density to a very high number density, it's about this low number density, this is high number density. We increase very high number density, we find that this black curve, we find that free induction decay is amplified to a maximum and then decrease to the negative part and have some oscillations. So this negative part comes from the emission reabsorption, and if we have this radiation pattern in the frequency domain, that is line splitting. And the most interesting thing is that when we choose a number density, it's in the intermediate number density. So the number density is not too high, not too low. We find that radiation is like this way. It's weak, but lasts a very long time. So if we change the number density and measure the lifetime of this radiation, we find that at the intermediate number density, the lifetime can be much, much longer than T2 time. So we try to explain it in this way. If we only have one atoms, and the coherence will be killed in T2 time. So that completely coherence is not there. So if we have two atoms or two or more atoms, so before the coherence is killed in T2 time, it can transfer its coherence into its neighbor atoms. So if in this way, if the coherence will just transfer many times, and in this way, if we want to kill the entire coherence of the entire system, we have to use much longer time. But this coherence transfer will require some energy to drive it. So if we have too many atoms, the coherence transfer is pretty frequent, and but the energy dumping is too fast. In this way, like the number density is pretty high, so we find that the internal energy of the population will dump too fast, so the coherence will die out in a short time. Okay, so this is another example about this cooperative radiation, that we do this calculation about 3-level system. With the same upper level, we prepare all the population in the upper level system, and it can radiate into two different down state. So it's very usual in the Rydberg transitions. And these two transitions have the similar frequency, resonance frequency, and very small different transition dipole moment. We want to observe that if we prepared all the population here, we use a very weak chirp to induce polarization at the same time, polarization of these two transitions at the same time. We want to know that how much energy will flow in this channel and how much energy will flow in this channel if they have very small difference of transition dipole moment. So from the dispersed fluorescence experiment, we expect that the intensity ratio of these two branch should be proportional to oscillator strength and proportional to the dipole moment, transition dipole moment square. And we set, in the calculation, we set this is 5 by transition dipole moment, this is 4 by. And we calculate the transition dipole, the intensity ratio. That is the same as oscillator strength prediction. But if we assume that is 5 kilodebye versus 4 kilodebye, that is Rydberg transition dipole moment, we find that at early time, it's not very far from the oscillator strength prediction. But with time is evolving, and more energy will be focused into these bigger, larger dipole moment transitions. And finally find that most of energy, maybe 99% of energy, will just flow in this channel, and very little energy flow in this channel. So we find that it is pretty strong number density dependence. So we vary the number density. We find that in a very high number density, and even the transition dipole moment is only 40% difference. That is a very small difference, and the intensity ratio of these two branch is about more than 100 difference. That is a log scale. So this is about more than 100 difference. So that means even that there are a lot of two possibility or even more possible transitions existed in your Rydberg system. If it's in a very dense Rydberg gas, it can always choose one maximum transition dipole moment to let the energy flow in this channel. So that the radiation is always nearly single mode radiation. So this is the third calculation, and we just we try to understand how the excitation pulse will propagate in an optical thick system. This optical thick system has large number density and very big volume. So the meter wave will propagate in this way. So we find that in the front part, if we use a pyro 2 pulse to induce polarization, in the front part is a regular nutation of pyro 2. But in the end part, it has some very complicated pattern. So this pattern is deviated from pyro 2 pulse. So if we use this electric field to calculate the induced polarization, we find that in the front part, we can induce a very large polarization. And at the end part, the polarization is nearly zero. It suggests us that maybe because this is zero, because the excitation pulse cannot penetrating into this big volume. So it suggests us maybe there are a very strong reflection wave. So because the energy cannot go here, so it's possible way it cannot go the side because retarded limitation. So it maybe there are very strong reflection wave. So this suggests us to make maybe a Rydberg mirror. So we can detect the radiation not forward but backward. So it's good for us because in this way it can separate excitation and radiation completely. And we can detect the fast process and the weak signal. So all of these 3 slides are calculation. And then I will show several experiment evidence that we suppose that is come from the cooperative effect. But unfortunately, our current experiment status is not so good because our supersonic jet with ablated molecule beam is not very stable. So we cannot get very high number density with our fluctuation of shot by shot is pretty big. So this is the highest number density we can get now. Just now I showed in the calculation is at least 10 to 6, but this is only 5 times 10 to 5. And it has more about 1 order magnitude fluctuation. So we have to improve that. So we put our highest number density we can get and use excitation pulse and observe free induction decay. And we find that 2 very different type of free induction decay. The early part is intense but short lifetime. And later part is weak but long lifetime. If we do the Fourier transformation of these 2 part of the radiation, we find that here is like a Lorentz line shape. Here is like a Gaussian line shape. Our explanation that this Lorentz line shape is homogeneous dominated superradius decay, and this is large. This is Gaussian line shape is come from the Doppler-Brownian free induction decay, regular free induction decay. And why these 2 existed is maybe come for a lot of reasons. Maybe the most simple explanation that our system is not so stable, so the number density distribution is not homogeneous, and the shot-to-shot fluctuation is pretty big. So in some situations, the number density is high enough to trigger the superradius, and so we can observe this one. And sometimes the number density is not high enough, so at the same time we see the Doppler-Brownian free induction decay. So this is the second evidence of cooperative radiation, that we know that coherence will encode the information in 2 different aspects. One is in the nutation, one is in free induction decay. So if we use pyro 2 nutation, that means the maximum coherence corresponds to maximum emission, the free induction decay. But pi nutation, that means 0 coherence and minimum free induction decay. But that is not always right in your experiment. In this spectrum, we maximum free induction decay and find that nutation is definitely not pyro 2. So, and we find that this deviation of this curvature is highly number density dependent. So we measure that systematically, we change the pulse area, we change the nutation shape, and we measure the free induction decay amplitude. In the low number density, we find that pyro 2 pulse will induce the highest number density, induce the largest free induction decay. But in the in the higher number density, we find that it seems not have a maximum point here and decrease. It's totally different. So our explanation is that if the number density is high, the cooperative radiation is dominated. So the radiation will modify the excitation pulse area, And this induced polarization will propagate in the big sample and generate a non-uniform polarization distribution. So based on these two assumptions, we do the calculation, and this curve is a calculation prediction. We find that it's basically consistent with our measurement. So this is another experiment we do. We want to show that is number density dependent cooperative radiation. So if we put the number densities pretty low, we find that there is a transition with single peak. And we increase the number density, we find there are two side peak appears. And we increase more the side peak separation more. Unfortunately, I do not know why there are 5 peaks instead of triplet 3 peaks. I think maybe the most possible explanation is that our system is not stable. We have to reproduce this experiment and improve our experiment conditions. But these splittings, and the splittings is going further and further, is reproducible. So and at the same time, if we measure the peak the frequency accurately at the center frequency, we find that there is some frequency shift from here to here. It's about several hundred kilohertz frequency shift. So these splittings, we want to explain the splitting first. The splittings is not very unusual because it's like a monotriplet structure. So different from monotriplet is induced by the external driven electric field. But these splittings is come from the radiation itself. So the shift, we want to explain the shift by the Stark effect. Because usually if the transition dipole moment is small, it's not very sensitive to the radiation, the electric field. But if we have a very large dipole moment here, it's very sensitive to a weak radiation electric field and shift the frequency. So we put our experimental parameters into these equations and find that the frequency shift should be several hundred kilohertz. That is consistent with our measurement. Okay, so it's almost done. All the experiment I have shown that is done in our current supersonic jet with ablation, with laser ablation beam source. This beam source cannot give us very high number density and have very large fluctuations. So we want to find a new technique can give us large number density, very stable molecular atom beam, and slow beam. It's slow beam that we can decrease our Doppler and increase our resolution. And fortunately, John Doyle's group at Harvard gave us such good technique is buffer gas cooling. And we do some preliminary experiment in our lab and find that it's just perfect for us and meet all of our requirement. So this buffer gas cooling works in this way. We just use the laser to ablate it or target molecule atoms in a cooling cell, in a 20 Kelvin cooling cell. And these hot atom molecules will be cooled down to collide with the buffer gas. In this cooling cell to 20 Kelvin, and then hydrodynamics expand into the vacuum chamber. And this hydrodynamic expansion will further cooling down the translation and rotation temperature to about 5 Kelvin. So the beam velocity of this apparatus, this technique is much slower than supersonic expansion. It's 100 meters per second. And in this way, the Doppler in about 100 gigahertz is smaller than 50 kilohertz. So the number density we have measured, the calcium atoms in our lab is about 10 to 12 atoms per pulse. That we can get the maximum number density is about 10 to 9 per cubic centimeter. And this is the ground state of the atoms. And if we prepare it for the Rydberg state, we can get maybe 10 to 8 per cubic centimeter. That is 2 order magnitude than our current maximum number density. So we believe that we can see very significant super radiance or cooperative effect, and shot-to-shot fluctuations is 5%. Okay, in the last 3 slides, I will discuss a little bit about extend our current technique, the buffer gas cooling technique and chirp pulse technique to the Rydberg molecules, especially for core non-penetrating Rydberg state. So we like the core non-penetrating state because it's very like a hydrogen atoms. It have a known energy, and have an analytical quantum defect expression with perturbation theory, and have very long lifetime. And if we do the induced transitions between the different core non-penetrating Rydberg molecules, we can record a pure electronic spectroscopy with fixed rotation quantum number and vibration quantum number of the ion core. So it's very sensitive to the DC and AC electric field, and alternation is slow and selective. So that this core non-penetrating Rydberg molecules is not only interested by the spectroscopist, but also it can do a lot of, it's very useful for fundamental physics study. So such like slow trapping and quantum manipulation, and we can use these core non-penetrating Rydberg molecules to prepare the selective low vibronic state of ion. So the first work to do this core non-penetrating state is how to prepare a large population of this core non-penetrating state. So here I propose two different schemes. The first one is use optical millimeter wave stereo experiment. So we started from D state with intermediate state of D state with laser populated to here, and we want to use the laser and millimeter wave pulse sequence to excite the G state. The G state is approximately a core non-penetrating state with longer lifetime. So if we want to go more, we can use a millimeter wave pulse sequence to climb up to even higher state. So, but the problem that's the F state. We have to use laser to climb up to F state first and to the G state. The F state always, because of the predissociation, the F state always have very fast, very short lifetime, maybe 1 nanosecond, maybe even smaller. So we cannot let the population stay at F state for a very short time. And we have to, what we want to do, use optical millimeter wave stereo, is just try to move the population from D state to G state directly, not touch F state. So we use a counterintuitive pulse sequence and overlap with 100 nanosecond laser pulse and millimeter wave pulse. To prevent the population accidentally touch the F state, we make the laser as off resonance excitation, and we use a chirp pulse to instead of the single frequency millimeter wave pulse. So in that way, all the population can always go upstairs, will not go back. So we do the calculation, find that if we change the lifetime of the F state, we find that even at 100 picosecond lifetime of the F state, we can still get about 40% of population transfer. So that is acceptable efficiency, population transfer efficiency. The other scheme to do is use the Stark mixing and adiabatic focusing method to do that. So we assume that a molecule have this quantum defect of the different L state, and we put it in an electric field, and we get this Stark manifold, and if we put the electric field as 10 volts per centimeter, we can find that the energy splittings is about 2.5 gigahertz. So in this way, we can use a laser to selective move the population maybe to this nominal H state here, and then turn off the electric field in a couple of nanoseconds and adiabatically. And this can meet the adiabatic requirement pretty well, and all the population will just stay in this state and move to the H state without electric field. So we do the calculation, find that if we put the 10 volts per centimeter here, and it has the large distributed mixing coefficient, and we turn off the electric field, we find that it can focus to the H state. That's what we want. And the key point of this part is determined by the quantum defect of H state. The quantum defect cannot be too large and cannot be too small. If the quantum defect is too large, we have to apply a very large electric field mixing with the Stark manifold. And another thing is that if the quantum defect is pretty large, the predissociation will just is shorter. So we cannot have enough time to turn off the electric field without significant predissociation. But if the quantum defect is too small, it's not good, because the energy spacing between the H state and the higher degenerate L state is very small. So it's pretty possible that we do not get a single final state, but a distributed final state. So that we have to choose appropriate quantum defect of the nearly core non-penetrating state. Okay, I'm done. I think in this talk I have introduced our chirp spectrometer technique and buffer gas cooling technique. We want to combine these two techniques to study the cooperative radiation and dipole-dipole interaction in the calcium atoms Rydberg system. And we want to use these two techniques to study the core non-penetrating Rydberg molecules. And thank you, I want to thank my advisor Bob and my colleagues and as a funding, and thank you for your patience.
Well, thank you very much for presenting this very interesting experimental technique, which I guess is also ideally suited for ion pair states. So I would like to open this for discussion. Wait 1 second. So it's open for question. Maybe I start with one. So with this density, you say you want to find the optimal density to observe this collective effect. So is that when the probability of absorbing one photon through the length of your sample is 1/2? Or is it too naive to?
You mean that is probability of observe
one single photon over the length of your sample is 1/2, or that you get the maximum effect, or?
Oh, it's determined by the geometry of your sample. If your sample is a long sample, that is this photon will very easy to be absorbed by another atoms.
Yes.
So, and build some correlations between several atoms. But if our system is flat, so it's very hard. We have to.
Yeah, you need a long.
Yeah.
Yes.
It's determined by the geometry of our system.
And it will be then being emitted in the same direction as propagation.
Yes.
But then, what is the principle of the mirror that makes it reverse? I just missed that point.
Oh, okay. So I mean that is two different type of experiment. For the superradiance or cooperative radiation, we want to use a very small excitation pulse that may pi over 1,000 pulse to induce a very small amount of photon numbers. And these photon numbers will just amplified in the sample and radiated in the forward part. And in the mirror part, we want to use a pi over 2 pulse. It's a strong pulse. And it induces a polarization. Yes. But this induced polarization cannot propagate into the end part of the sample. So maybe we want to find that where it will go. So maybe it will come back. So that means a very strong absorption means a very strong reflection.
Not sideways, or you think it has to go back the way it came?
Yeah, we think that it should be go forward and backward. It should return time will just limit it to the side.
All right. Okay, thank you. So there are now a few more questions. So maybe I start here with Ed Eiler.
Okay, this is really a follow-up on your first question, going back to the modeling of the superradiance and subradiance. It's probably just a question of understanding what the Bloch equations are telling you, but I didn't quite understand why, if you get coherent transfer of the excitation, that actually prolongs things. Because if you get a perfectly coherent transfer of the dipole, it seems like you would still have a superradiant system. Is there a phase shift that causes the increased lifetime?
I think our explanation about this subradiance is that its number density is not high. The coherence transfer and the coherence transfer is not high frequency enough to dump the energy. So if the energy dumping is pretty fast, that is superradiance. That will definitely shorten the lifetime. But if not you see that this calculation is for superradiance is pretty strong peak, but here is weak. It can last. The energy dumping is pretty slow, but can last longer.
Yeah, I guess I'm still not sure I see quite why it happens, but I do believe that's what the Bloch equations are telling you, so it's probably right.
So there was a question by James Schaffer. No, oh, sorry, I thought you'd raised your hand. So then Adam.
Thank you. So, I was wondering, so do I understand correctly that with the microwave source now you can populate specific states, and could you then in principle populate 2 or more states with a specific phase difference as well in the population?
At the same time, or? At
the same time, yes.
Yes.
So you can have superposition states with defined phase between the different component states. Okay. So in principle, you can have extremely fine control of, say, the state of the ion core, if you wish.
Yes.
Okay. That's fascinating. Thank you.
So further questions? So your comment about the quantum defect, at the end I missed. So you say, I understand that if your quantum defect is very small, it can be a problem. But when you say when the quantum defect is large, you will have predissociation.
Yeah.
And to me, it's not obvious why there is a direct correlation between the quantum defect and the predissociation rate.
My understanding is that if the quantum defect is bigger, that means the electron will spend more time in just collide with strong interaction with the ion core. So I think that will induce predissociation. If the quantum defect is 0, so that means like a hydrogen atom. So that is not, the electron will not interact with the ion core. But if the quantum defect is bigger, is more and more bigger, my understanding is that the electron will spend more time to
So you are talking about not the modulo part of the quantum defect, but the total quantum defect.
Yes.
Yeah, okay. Yes.
When you showed this excitation with the laser photon plus the microwave, you mentioned the connection to Stirap.
Oh, the last one? Okay.
Yeah. How well would you do if you just thought of it as a 2-photon transition with an off-resonant intermediate state?
We try to do this calculation, and we change what we do is that we change the lifetime of the F-state lifetime. We find that this method is significantly better than the 2-photon.
By this method, you mean including the chirp, or the timing is important, or both?
Including chirp and even that if we do not use chirp and off resonance, it's still better than 2-photon directly.
So the pulse timing is important?
Yes, the pulse timing is important. Now our problem that the millimeter wave is very easy to make 100 nanosecond, and now the laser is not very easy. But if we choose the pulse length is 100 nanosecond, that is best.
So to make a 100 nanosecond pulse, you can use a Titan sapphire laser and amplify it, or make a reflection of your pump YAG laser and recombine so that you have a 100 nanosecond.
So with different delay and
yes. So I see no further questions. Let's thank again our speaker.